Hello friends, we have seen the development finite element modeling of bar element or elements which can ensure the continuity of the variable of the basic variable of the differential equation. Also we also refer to it as the element of C0 continuity, that is 0th derivative is continuity of 0th derivative is maintained across the boundary inter element boundaries. And eventually we have gone through the complete derivation, complete formulation of the element, and then the assembly, how the domain is discretized using different finite small elements, and then develop finite element approximation over each element. We took the example with respect to 2 node element, that will be these 2 nodes. Interpolation model of primary variable between these 2 nodes will be a straight line, so linear polynomial. So these linear polynomials they ensure the continuity of the primary variable across the inter element boundaries, that will be through the shared node. And once the element level equations, equilibrium equations are established, those are assembled into a global system of equations, and after that global assembly, whatever the specified essential boundary conditions are there for the problem, those are imposed using this very simple penalty function approach, or the stiff spring approach as it is called. And once this is incorporated, the essential boundary conditions of the problem are incorporated, then the system of equations can be solved, and we can find the solve the system of equations for the unknown variables. And with these unknown nodal values of the primary variable known, we can go back to element level equations and find out the secondary variables that are of interest for the problem. Now, for the simple problem that we have seen here, we only referred to the finite element mesh, which was only straight line. The entire problem, entire domain was a straight line. All the elements that we used, 4 elements that were in the same line. So, the same frame of reference could be used for defining the element level equations for all the elements, but that is not true in general, and we may have elements which are different elements with arbitrary orientation. For example, a simple truss bridge. So, this planar truss comprises of several bar elements which are interconnected through hinged connections, and they together support the transverse load. These kind of structures are very common for in the trussed bridges. I mean, you might have seen several such trussed bridges during your travels on railways, Indian railways. So, the point is these kind of different elements. So, this is one element, this is another element, this is another element. So, these different elements have different orientation, and obviously it is easier to define the element level equations when the axis is oriented along the member length. Then these equations are there is only one variable which defines, and transfers to the axis, the displacements are 0 because all the loads are in along the axis. So, it is easier to define the element level equilibrium along the individual member axis. Those are called local frame of reference or local coordinate system. But for example, if I use one local coordinate system for this element, let us say element 1, and another coordinate system for the second element. So, this element, let us say element number 2. Now, the frame of reference is of course different, and the equations, the assembly cannot take place immediately. We cannot compare apples with oranges. These are two different frames of references. So, before we can assemble the contributions or element equilibrium equations for different elements into making a global representation of the total structural system, it is necessary that these local equilibrium equations, element level equilibrium equations in the local frame of reference, they are transformed to a new frame of reference which is held common. So, this is the global frame of reference, common global frame of reference. So, all element level equilibrium equations are transformed with respect to this. So, this is same as the change of basis that we had earlier seen during our discussion of vector spaces. So, the element level equations are transformed to this new basis, and then once all the so the element level equations, they are transformed to this global frame of reference, and then they are used for assembly of equations. So, that when we go element by element and go through the entire structure, after transformation, they are all element level equations, they are referring to the same frame of reference. For example, in this case a generic element E oriented at element angle theta. So, this u bar and v bar, these are the local degrees of freedom. So, u bar I and uj bar I, these are the along the axis, along the local member axis, these are the deformation, and v I and vj, those are the transfers to the member axis. Now, these are to be related to the global the degrees of freedom in the along the global frame of reference. So, that is u I and v I at node I and u j and v j at node j. The member itself is oriented along with respect to x, the local x axis of the member is at an inclination of theta with the global x axis, as you can see here. So, the whole problem is relating these local frames of local coordinate local degrees of freedom along the defined along the local coordinate system with to the degrees of freedom at each node along the global coordinate system. So, it is a 1:1 mapping. So, I mean there are 4 total degrees of freedom in local coordinate system, and those are mapped to 4 degrees of freedom in all for 2 nodes in the global coordinate system. And once this is done, this equation of equilibrium for each element, they are referring to the same frame of reference, and then the element assembly can take place and problem could be solved. So, as I said, it is convenient to formulate element equilibrium equations with coordinate directions oriented along a member local coordinate system, but we cannot use this because different elements will have different local coordinate system. So, we cannot use different local coordinate system and mix them together. So, different members as a, might have different orientation in a structure, and therefore, it is necessary to transform the element equilibrium equations to a common global frame of reference before the assembly of element equations. And after the assembly, as we did earlier, we impose the boundary conditions, essential boundary conditions, and after the imposition of essential boundary condition, the system of linear simultaneous equations are solved for the unknown variables of the displacements or the primary variable at the nodes of the structure. So, this in effect completes our discussion of finite elements of C0 continuity. In structural mechanics, it can be used to model these truss or rod kind of problems, or even torsion of a circular shaft that can be modeled using this element, because the governing differential equation is second order differential equation, and the weak form, the highest order of derivative in the weak form of weighted residual statement is the first order, and therefore, a linear interpolation between 2 nodes, primary variables defined at 2 nodes, is sufficient to provide a work approximation of the problem. The weighted residual statement exists, and we can get the system of equations from the weak form of weighted residual statement. Now, similarly, it can be also used for other fields of application, for example, electrostatics or heat conduction, or even the flow through porous media. So, they are all governed by the similar second order differential equation, and this C0 elements can be used for modeling the problem and finding useful approximate solutions. Now, that is crucial point. Finite element solution is an approximate solution to the governing differential equation. The moment we talk about approximate solution, the natural question that arises is how good is the approximation, and can I believe in this approximation, can I believe in the quality of approximation that I am getting. So, we will come to that what makes the complete finite element solution, the approximation, what makes it working approximation, and what are the steps to ensure that the approximation is good and it is converging to something meaningful. But before that, let us recapitulate the entire process of finite element analysis the way we had done. So, we identified the first is the identification of the physical domain and a problem statement, what is the problem that we are trying to solve and what is the domain of the problem. So, the boundaries have to be fixed first. Then it is the derive the governing differential equation, find out what is the applicable governing differential equation for the problem, what is the domain of applicability, and what are the associated boundary conditions for the problem. And once we have these, we develop the weak form of the statement of weighted residual for assuming, for some approximate, some approximation. So, we will always have some errors or residuals, and then we develop the weak form of weighted residual statement for the domain residual for an approximate solution. And from the boundary term of the weak form, we find out or we can identify what are the primary variables and what are the secondary variables of the problem. Now, this is very important because the finite element approximation has to be an interpolation model, polynomial approximation has to be in the form of interpolation between the primary variables. So, it is absolutely crucial to identify what are the primary variables, and this becomes, this is not always the same as the unknown function of the governing differential equation, as we will see in the next part of this lecture very soon. So, identification of the primary and secondary variables of the problem from the boundary terms of the weak form, and knowing the identifying the interpolation primary variables, we can find out what is the type of interpolation that is required, and hence the type of finite element that will be required for discretizing the domain. And once we find out what is the approximation, what is the kind of interpolation model that is required, and what is the kind of finite element that will be required for approximate solution of or finite element modeling of the problem, then we develop the finite element mesh and for the discretization of the domain. So, the entire domain is divided into a number of finite elements and interconnected through nodes, and then we construct polynomial interpolation for primary variables over one element at a time, establish the element level equations by evaluating the weak form of weighted residual statement over the element by using Galerkin approach and using interpolation functions or the shape functions as the weighting functions. And once we have these element level equations, we can assemble them into the global level of equations, and also at the element level equations we also impose the natural boundary conditions, whatever are the natural secondary variables, if those are prescribed, those are imposed at the element level equation, and subsequently the element level equations are assembled into global system of equations, and then the essential boundary conditions are imposed on the global system of equations. And once the essential bound, and of course the assembled global system of equations, if any transformation is required, that has to happen after this point, after the imposition or secondary variables or natural boundary condition, and then the element level equations are transformed to global frame of reference, and then they are assembled into global system of equations before the essential boundary conditions are imposed. And after the imposition of essential boundary condition, the simultaneous equations can be solved for unknown primary variables at the nodes of finite element mesh. And once we find the finite element solution for the primary variables, the secondary variables and other derived quantities of interest may be computed by reverting back to element level equations with known values of the primary variable at those nodes of the element. So, this in essence is the entire finite element process. The difference only happens, I mean, for different problems, as I said, different problems we have different kinds of interpolation functions and different types of finite elements, but rest of the process remains the same. So, it is a pretty straightforward, very structured process and very easy, very I mean well suited for automatic computation, and that has been the reason for the phenomenal growth of finite elements which coincided with the development of computer technology. Although the concept of finite elements, similar concepts had been known since the days of Gauss, but for the lack of automatic computational tools, the method could not find much following. But in the middle of the 20th century, when tremendous growth happened in the development of computational computers and computing technology, that provided the right platform for development of finite element method as well, and from then onwards the finite element method has grown tremendously, and this is, I mean, almost to the extent that it is now the de facto standard method for engineering analysis for any CAE problem. Now, as I said, finite element analysis, finite element solutions are an approximate solutions. So, an approximation can be a good approximation, it can be a bad approximation, and our results or any subsequent engineering can be only as good as the results of the preliminary engineering, I mean analysis. If my analysis is wrong, if my computations are wrong, any subsequent decisions, any subsequent designs on the basis of that are obviously going to be completely wrong. So, it is absolutely essential to be very sure that our finite or any approximate solution, including finite element solution, is a good approximation and the error is within control. So, what ensures, what is the basic requirement that one has to observe before we can say that the finite element analysis, the solution of this that we get from a finite element analysis is acceptable. There are certain rules for construction of approximation or finite element approximation, and we will go through those rules first. So, the first requirement is of course continuity of primary variables within the element. So, obviously within the element, the variable that we are approximating, that has to be continuous, that is the that is automatically achieved by using interpolation model. And because we are using interpolation model and different elements connect with each other through shared nodes, and the primary variables at those nodes are also shared. So, the continuity of the primary variable is also ensured across element boundaries. So, this may not appear much of a problem in the case of simple one dimensional problem, which are only defined by using single nodes. Boundaries are defined by single nodes and nodes are shared. So, everything is shared. So, the continuity is ensured. The problem is little more tricky when we talk of 2-dimensional and 3-dimensional finite elements. So, for modeling the 2D and 3D continuum problems. So, continuity across the element boundaries is not as trivial as in the case of 1-dimensional finite elements. So, second thing is compatibility between adjacent elements. So, the again a finite element mesh, there should not be any gaps or even overlap or anything. So, the domain compatibility, they have to be, there should not be any under representation or over representation of the domain of the problem, original problem, while discretizing the finite element mesh. Then the completeness of polynomial approximation for the primary variable. So, when I say completeness of the polynomial approximation, let us say in this 2-dimensional 2 node element, we said that it has first degree polynomial. I mean 2 variables and interpolation can be defined by using a first degree polynomial. So, first degree is the highest degree of polynomial term. So, now first degree can also be just first degree term x without the lower order term, that is a constant. A complete polynomial would be a constant term a0 plus a first degree term, that would be a1, that is coefficient multiplied by x. So, the complete approximation would be a0 plus a1 x. So, that is complete up to the first degree. Now, I cannot, it is not possible to start ab initio start the polynomial approximation using just x, and maybe because I need to have 2 terms. So, I can maybe I can start with x square if possible. So, a1 x plus a2 x square. So, 2 term approximation, that is not a valid finite element approximation. It has to be complete, approximation has to be complete starting from the lowest order term, and that in this case is the constant term 0th degree polynomial. And why so much emphasis, why am I dwelling upon on this completeness requirement? See, the point is if let us say this is the truss element and a bar element, and if there is no restraint, then this motion, any push here would lead to the entire bar moving as a whole without any deformation, without any strain developing in the body. So, this is what we call as rigid body motion. Now, this rigid body motion of this bar is not possible in the finite element solution unless I include that constant term, because that constant term is what allows the displacement to have a constant value all through the domain, each point, right. So, if that constant term, possibility of this constant displacement is not there in the approximation, then there is no way I can model, I can include a rigid body motion in the model, finite element model. And even if the body is subjected is under no constraint, so there is not going to be any strain in the body if under the when any force is applied, because it has to move without any restraint. So, even in the case of no restraint, the model would predict strain in the element, which is obviously wrong. That is why it is important for rigid body motion to be captured, and also at the other end, let us say this finite element is of this size, but I can keep on discretizing, and in the limit I can come to a very infinitesimal length theoretically, right. So, infinitesimal length let us say approaching the point. So, what is the value of the strain at a point? Strain at a point is a constant. So, that constant state of strain should also be present. So, these are the 2 bare minimum requirement for finite element approximation. Rigid body modes should be the finite element approximation should be able to represent the rigid body modes, and the finite element approximation should be able to capture the constant state of strain, which would be the case in the limiting case of element size shrinking, I mean as I refine the finite element mesh and reduce the element size smaller and smaller and smaller and smaller, I mean I cannot reduce it beyond a point. So, but at a point if the element size is so small so as to be comparable to a point, the strain at that point is a constant value, and that constant value, constant state of strain should be captured in the finite element approximation. And that means when I say constant value of strain in structural mechanics problems, of course all my examples would be from the domain of structural mechanics. So, that constant state of strain necessitates inclusion of linear terms. So, first the constant term, so that is the 0th order term, 0th order polynomial, 0th degree polynomial, and the first degree polynomial term. These are the bare minimum that is required in any finite element solution for structural mechanics problems of C0 continuity. If these two terms are included, then the convergence will happen, and it will be monotonic convergence, and we will get better and better as you can imagine. As the element size is decreasing, it is approaching constant state of strain, and if the element approximation is capable of representing that constant state of strain, we would be approaching the true result in the limiting sense, and the finite element solution would converge to a true solution in the limit. And then finally, the finite element approximation should be consistent with the constraints of the problems. For example, if there are two different fields of displacements or deformation, and there is required to be some relationship between these two fields, then the approximation that we use should not contradict, should not go against those relationship, those basic physics of the problem, that has to be honored, that has to be adhered to. So, this is very commonly observed. I mean this problem consistency requirement is very crucial when we come to the problem of shear deformable systems or shear flexibility, shear flexible models. We will talk about it in greater detail as we come across that problem. Thank you.